Okay. So today we have Samik Basu continuing his series of talks. This will be his last talk today.
Okay.
So you'll be talking about Atiyah duality, is it? Yeah.
All right. So I want to talk about Atiyah duality, and and it is a follow up from what we were doing in the last lecture, which is Spanier Whitehead duality. And in the end, remember, we had this nice relation between the uh, Spanier Whitehead dual of a finite space and the complement of the space with respect to an embedding in a sphere. So we will carry the story forward, but I will introduce two new aspects in stable homotopy theory in this lecture. One is the concept of Tom spectra, and the second one is the what is called the Poincaré in Tom construction, which will basically relate uh, starting from relate the Spanier Whitehead duality statement to Atiyah duality. Okay, so these I should say that these are uh, really the heart of classical stable homotopy theory, which uh, one of the major successes was to relate stable homotopy theory to differential topology, and this Poincaré Tom construction and Tom spectra are real avatars of that. But now we have can view them in new lights as well. But I will not go into that story. So I will. So this is basically the classical story of uh, Tom Tom spectra from the view point of view of orientations. Okay, so let me begin. So the so mainly most of my lecture will at least half of it will go into the definition and properties of Tom spectra. So the Tom spectra basically the concept arises from the Tom space of a vector bundle. So Tom space of a vector bundle. What is it? So if V is a vector bundle over X, V is a vector bundle over X, then what you can do is you can you can form a sphere bundle by taking the fiber-wise one-point compactification. So the fiber over each point is a copy of Rn, where n is the dimension of the vector bundle, and you can take a fiber-wise one-point compactification. So fiber-wise uh, one-point compactification, point compactification will give you a sphere bundle with fiber Sn. Compactification gives you a sphere bundle which I denote by S to the V. So if V was just Rn over a point, S to the V is just Sn. Okay. What are the properties of this S to the V? There is a infinity section because um, the point at infinity uh, gives a section of this fiber-wise one-point compactification, which I denote by S. This goes from X to S to the V, and um, we can define the Tom spectrum, Tom space, the Tom space of V as the cofiber of this map. Cofiber. So cofiber means homotopy cofiber, but you see that the inclusion of X in S to the V is already a cofibration. So that's just same as the usual um, quotient space co-fiber of S. Okay. When you define it like this, you easily see that there are many other ways of making the same definition. So there are other definitions of the same thing. Uh, the for so one is, suppose if you have X is compact, so over a compact space you can actually, over a paracompact space, you can give a inner product on V. You can put an inner product on V, and then you define D of V to be uh, all all elements of norm less than equal to 1. This is the disk bundle. This is the disk bundle, and S of V is the sphere bundle. This is all vectors of norm 1. Norm 1. This is the sphere bundle. And in these terms, the Tom space is just the disk bundle mod the sphere bundle. Oops. Yeah, the Tom space of V is just the disk bundle mod the sphere bundle. Okay. So, so I mean, how do you identify the two? It's same as saying that if you take this, yeah, you can just so it's so in a sphere you can collapse the lower hemisphere to the point. It is like doing that identification here between the two. So that's one way of giving the definition. Um, another way is what you can do is you can so you also have the zero section to every vector bundle, right? Zero section. Now this is from X to V, which maps X to X comma 0 belonging to the fiber at X. Okay, so this so you have you can take V minus the zero section, and you can put it inside V. So this so this is an inclusion, and the homotopy cofiber of this is also the Tom space. Homotopy cofiber is also the Tom space of V. Okay, so that's one more way of saying it. And another way is you can, if X is compact, then then the Tom space of V is just the one point compactification of V as a space. Is the 1-point compactification of V. Yeah. So so that's another way of saying it. So an example is if you take the trivial bundle X cross Rn to X, if you take this trivial bundle, then the Tom space is going to be just the nth suspension. So I mean, if I just calculate it directly, this is going to be x cross Sn mod x cross the point at infinity, right? That's by definition, but you can write it as a n-fold suspension of x with a disjoint base point. Okay, that's a homeomorphism. Okay, now when you look at a course in algebraic topology, um, no, this is not going to be in the first course, but if you look at orientations of vector bundles, how is the orientation of a vector bundle defined? It is defined to be a class in, if you look at Milner and Stasheff, let us say it is defined to be a relative class in V comma V minus 0 section, such that the inclusion, it pulls back to the generator of Rn comma Rn minus 0 and under the inclusion of every fiber. So so this V comma V minus 0 section, by this definition 2, you see that that is related to the Tom space. So you can equivalently say that that's a class in the Tom space, such that when you pull back to every fiber, this is going to be a generator. So you see another an orientation definition of orientation can be like this. So V is orientable if there exists a class alpha in, so I'm assuming n to be the dimension of V, Hn of the Tom space of V, such that for each fiber, for each fiber, see, for each fiber you will have a, see, if you have a, so each fiber will be look like this. So it will have a point. So here you have x, and over here you have the, you have, so associated to x you have the Tom space of the vector bundle. Okay, let me not get ahead of myself. So this is the vector bundle V, and if I pull it back to the fiber, I will get Rn, right? And now you can take Tom space on both sides, so that will give you a map from Sn to Tom space of V for every fiber. So for every fiber, uh, alpha pulls back to a generator of Sn, to a generator of Hn of Sn. Okay, so that's another way of saying, giving the definition of orientable. And in these terms, um, you have a nice way of writing the Tom isomorphism theorem. So Tom isomorphism theorem, you can write it very nicely. What you can do is this. So what you can do is, so Tom isomorphism theorem will be uh, written like this. So I'll write it in homology. So this you will say like this. So V orientable. This implies that uh, Hz. So this is Eilenberg-MacLean spectrum with, for Z. Hz smash the Tom space of V is equivalent to Hz smash Tom space of the trivial bundle, which is sigma n x plus. Okay, so that's the, so it is a weak equivalence of these two spectra. So that's the Tom isomorphism. And how will you prove it using this class alpha? This class alpha is the Tom class. How will you prove it using the Tom class? You have to make a you have to notice something. Um, so there is a step here. See, what you can do is you can look at x cross x. Okay, over x cross x, I have two projections, pi 1 and pi 2, down to x, and you look at the pi 2 upper star of v. All right, and now if you pull it back along the diagonal, then this pulls back to the vector bundle v, right? Because delta followed by pi 2 is just the identity. Now, this will tell you, this will tell you, this will give you a map from the Thom space of V to the Thom space of phi 2 upper star of V. But now you can see that now you can prove something about Thom spaces. Okay, this is a property about Thom spaces which you can prove. That if I have vector bundles V to over X and W over Y, then I can form the vector bundle V cross, let me write it like this, box cross W over X cross Y. Okay, so this is basically you, or I should say box sum also. I think that would have been more accurate, but let me just write it like this. So basically over a point x comma y here, the fiber is the fiber at x, direct sum the fiber at y. Fiber of v at x, direct sum the fiber of w at y. And in this case, you can figure out that the Thom space of um, this box cross w is the smash product of the two Thom spaces. Thom space of w. Okay. So now this pi 2 upper star v is nothing but the pi 2 upper star v, now you can see, is going to be the box cross of the trivial vector bundle of dimension 0. So I'll just write it as a point with v. And the trivial vector bundle of dimension 0, if I take the Thom space, then the Thom space is just x plus. So this is nothing but x plus smash the Thom space of V. All right. So now what you can do, what you get out of this is that you get a map from the Thom space of V to x plus smash the Thom space of V. Okay. So this is not yet, we have not used anything about the orientation as yet. This you get automatically. That is, this is just because of this commutative square here. You get this map from Thom space of V to x plus smash Thom space of V. And then the Thom isomorphism theorem is that so the Thom isomorphism map can be written like this. You start from, so you start from Thom space of V smash hz, and then you apply the map from Thom space of V to x plus smash Thom space of V. So this goes from x plus smash Thom space of V smash hz. Okay. Now you apply the map alpha. Okay. So this is identity smash alpha smash identity. See, alpha belongs to h upper n of the Thom space. Okay. So that means this can be represented by a map from the Thom space of V to sigma n hz. Remember how we represented cohomology from last time. So such an alpha gives you a map from th of V to sigma n hz. So I will get a map from this, so that gives lets me go to this smash sigma n hz smash hz. Now you use the ring structure on hz. So you can use the multiplication on hz to now go from here to, and this sigma n will come out. So this will be sigma n x plus smash. Now this is the using the multiplication on hz smash hz to hz. So it will go like this. So I get a map. So this class allows me to construct a map like this. So such a map is exists for any such class, but the property that it restricts to an orient to a generator on each fiber may be used to show that this is a weak equivalence. Alpha is orientation class or Tom class. We called it Tom class. Alpha Tom class implies this is a weak equivalence. Okay, so that's the Tom isomorphism theorem, written in using Tom spaces and stable homotopy theory. Okay, so let's go ahead. The next thing I want to talk about is the Tom spectra. Okay, so here remember we had this. Let me just write it in a box here. So remember we had this fact from the previous page that if I take the Tom space of V box cross W, this is the Tom space of V smash Tom space of W. So if I have if I take the Tom space of V direct sum a trivial bundle, that will be equivalent to the, so trivial bundle I can write it as uh, just write it in this box cross notation by just taking box cross with r to the point. So this will be equivalent to S1 smash th of V, or the expansion of the Tom space, right? Okay. So for the Tom spectrum, let's start with the universal example, which is, if you look at BON, and BON, you know, this classifies vector bundles of dimension n, and you look at the universal bundle, and let's call that gamma n. Okay, so this is the universal n plane bundle, n dimensional bundle, and then you define MON to be the Tom space of gamma n. Okay, now you see, now you look at this, you put this BON inside BON plus 1. So so to classify a map like this, I should tell you, I should give you a n plus 1 dimensional vector bundle over BON, and that is just given by the universal n dimensional bundle direct sum a trivial bundle. So in other words, the universal n plus 1 plane bundle will pull back to the trivial gamma n direct sum epsilon under this, and let's call this in. Okay, so this square gives me a map from space of gamma n direct sum epsilon to the Tom space of gamma n plus 1. So in other words, I get a map from the suspension of MON to MON plus 1. All right. So these give you structure maps of a spectrum which I call MO. So these give you, so from here you get structure maps of a spectrum MO. Okay. So the nth space is this Tom space of gamma n, and you have these structure maps suspension MON to MON plus 1, right? So this is called the Tom. This is the example of a Tom spectrum. Okay. And this was very important. This was very important because of the following theorem of Tom. Theorem of Tom. This says that if I take pi k of MO, this spectrum, this is isomorphic to the set of k dimensional closed manifolds up to cobordism. Okay. So I don't think I will give you an idea about why this theorem is true, but but let me just tell you how this how to get a homotopy class of MO from a k dimensional manifold. So if I have, if M is a k manifold, so the, so this is the map in that direction. So this is given by like this. So if I have a k manifold, and then what I can do is I can embed in a large dimensional Euclidean space, which I write as R n plus k. Okay, n is large. Okay, so I can always do this. So now, so I can embed it like this, new. So so I can then apply the tubular neighborhood theorem. Neighborhood theorem, which says that this M is contained in some tubular neighborhood U, which is like the uh, disk bundle of the normal bundle of nu. Let me just write it as the n of nu, which is stand for the normal bundle of nu. So this is the disk bundle of the normal bundle, and this M is the zero, is embedded as the zero of that Rn plus k. Okay. Now I can do a construction which takes me from Sn plus k to the Tom space of the normal bundle. How? I will look at uh, points in, so this I now apply, I identify as the disk bundle of nu mod the sphere bundle of n of nu. Okay, so points in U map to the corresponding point here, and points outside U, this map to infinity. So that's the image of this sphere. Okay, this construction, this is called the Poincaré Tom construction. This is called the Poincaré, sorry, this is the Poincaré Tom construction. Okay, so this gives you this map. So I get a map from Sn plus k to the Tom space of the normal bundle of nu. All right. So that's the upshot. Now I classify this normal bundle of nu using my classifying map. So I can realize this n of nu will come from a map. So this is a so remember its dimension is what? This dimension m was a k dimensional manifold. So this dimension is capital N plus k minus k equal to capital N. So this gives me a map from which classifies the bundle from M. Um, let me write it like this: M to B O N, such that the pullback of the canonical capital N plane bundle is this normal bundle, right? So that gives me a map from the Tom space of the normal bundle to the Tom space of gamma n, which is MON. Now, if composing these two maps, yeah, sorry, now I compose these two maps. So that gives me a map from Sn plus k to MON, which after I stabilize gives me an element in pi k of MO. Okay, so that's what we were looking out for, because in the previous page, um, not this one, the next one, yeah, see we were Tom theorem says that pi k of MO is isomorphic to k dimensional closed manifolds up to cobordism. So I started with a k dimensional manifold, and from here I got a map from Sn plus k to MON, which stabilizes to give me a k dimensional homotopy class of MO. Okay. So this is why the Tom spectra becomes important. So what are Tom spectra now? So we can form a more general construction. So we have a general construction now, inspired from what I said 1 minute back. So the general construction is you have a map from X to BO. Let me write it as F. You define Xn to be the pullback, Xn equal to pullback of Xn to X, and this is BON. So BO is the direct limit of the BONs. Okay, so this is this pullback is the Xn, and so you have this Fn from Xn to BON, the pullback of F, and then now you write this Tom spectra of F, the nth space to be Fn upper star of gamma n. You take the Tom space of that vector bundle. Okay, and the same logic as before yields a spectrum. Yields a spectrum. Okay, and using this, so this is called the Tom spectrum of the map. This is called the Tom spectrum. Tom spectrum of F. Now there are many examples of such F which are of interest. For example, you can start from BSO to BO, and this gives you a spectrum MSO, and this classifies, I mean, the homotopy groups are pi k MSO is oriented K manifolds up to cobordism, K manifolds up to oriented cobordism. Then you can take BU, so BU to BO, so that's formed out of UN to O2N. That gives you spectrum, which is called MU. This is the spectrum of complex cobordism, and um, these pi k mu are the complex cobordism groups. Complex cobordism groups, and so, and another interesting case is what happens if you take the point to BO. Point to BO, that is that gives you the sphere spectrum. That gives you the sphere spectrum, and this also can be realized as a cobordism theory. This is called the homotopy groups of the sphere spectrum are the framed cobordism groups. So this really goes back to classical stable homotopy theory when this is actually a theorem of Poincaré, and at that time, using the classification of 0, 1, and 2 manifolds, you could calculate um, the 0, 1, 2 dimensional homotopy groups, the sphere spectrum. So this is so now let me come to what I want to say. So I will restrict now to finite complexes. Restrict now to finite complexes X, to finite complexes X, and then a map from X to BO F. This classifies a virtual bundle of dimension 0. This classifies a virtual bundle of dimension 0. Now why? Because I mean this maps from X to BO. If X is a finite complex, this is just a direct limit of maps from X to BON, and when you go from BON to BON plus 1, it takes gamma to gamma direct sum 1. So you are basically identifying gamma with gamma direct sum 1, and that is same as saying that uh, you are looking at bundles up to adding a trivial bundle, and so in a way you are just actually classifying virtual bundles of dimension 0. So so what is a virtual bundle? You can write it as V minus W, where V and W are vector bundles. So virtual bundle means that it's a element of the group completion of vector bundles, or the K theory group. So these are V. So you can write it as V and V minus W, where V and W are vector bundles, and dimension 0 means that dimension of V minus dimension of W is equal to 0, right? Now there is a property of finite complexes, is that given a vector bundle V over X, so X finite complex, then there exists W such that V direct sum W is a trivial bundle. Is a trivial bundle. That means X cross sum of n. This is a property of finite complexes. So every virtual bundle you can write as every virtual bundle may be expressed as some E minus so virtual bundle of dimension 0 may be expressed V minus dimension V for some vector bundle V. because if you have v minus w, you can just take some w hat such that w directs some w hat trivial bundle, and so then it's like v directs some w hat minus the dimension. So you can write it as v minus dimension of v. But the important observation is that the observation here is that in this case the Tom spectrum, in this case the Tom spectrum is is equivalent to sigma minus dimension of w, dimension of v, the Tom space of v. Rather, I'm just using the space. I should really say suspension spectrum of the Tom space, but let me just write it like that. Okay, I'm just identifying spaces with the suspension spectrum. I was also doing it earlier. So this so the so this observation. So there is no problem with respect to this observation. Now you can actually define it for any virtual bundle. So you can actually Tom's define Tom spectra for any virtual bundle, for any virtual bundle. Okay, how you just if you have a virtual bundle v alpha, you take alpha minus dimension of alpha, that's a virtual bundle of dimension 0, and you define the Tom spectrum of alpha to be sigma dimension of alpha, Tom spectrum of alpha minus dimension alpha, right? That is something you can do. Now the next thing is orientations. Orientations. So a Tom class. So now alpha is a virtual bundle, and now you can just make an analogous definition of the Tom class. So you can, but you can also, yeah, you can make an analogous definition like this. So Tom class uh, for the Tom spectrum of alpha is the same, is equal to, this belongs to the dimension of alpha, Tom class of alpha, Tom spectrum of alpha, and so this, so so you just, so we define it for the, for, so if this is of dimension 0, so if dimension of alpha equal to 0, that's the important case, because of, others are just related by a suspension. So um, so then you just look at something like this to be like this. So I have x to bo, this is the map which classifies the bundle alpha, and then I remember I defined these pullbacks in the definition, and this was alpha, this I'll write alpha n. So um, so this commutative square gives me a map from sigma minus n of Tom spectra of, so this gives me a map from the Tom sigma minus n of Tom space of Fn star alpha n to sigma to the Tom spectrum of, sorry, not Fn, what I'm writing. This is alpha n star uh, gamma n to the Tom spectrum of alpha, right? Because this Tom spectrum of alpha n star gamma n, this is the nth space of the Tom spectrum of alpha. So the nth space, if something is the nth space, you have a spectrum map from sigma minus n of that to that spectrum in the homotopic category. Okay, so this theta is a Tom class for alpha if I take this, if I call write this I x to xn to x as in, if in upper star of theta, this now is an element of this belongs to h0 of uh, sigma minus n this alpha n upper star of gamma n, but that's h upper n of th of alpha n upper star gamma n. So if in star theta is a Tom class for alpha n upper star of gamma n. Okay, so this one makes sense because so this last statement you see, this last statement you see only relies on the space level data because this is actually terms of an actual vector bundle. Okay. Uh, Another comment here is the Tom isomorphism uh, is a Tom class. This is entirely analogous. The Tom class theta induces an equivalence of spectra from Tom spectrum of alpha smash 8z equivalent to the suspension of dimension of alpha x plus smash 8z. This is entirely analogous. Okay, and the proof is also going to be entirely analogous. So these are the backgrounds on Tom spectra which I would need, and I see that I am almost out of. I think I have some. I started a few minutes late, so I think I will take 10 minutes and then I will stop to say what Atiyah duality is. So these are all the backgrounds from Tom spectra, and the remaining is going to be an easy application of what we did last time. Okay. So now let me go over to Atiyah duality. Atiyah duality. Okay. So remember from Spanier Whitehead duality we observed the Spanier Whitehead duality from last time. Whitehead duality gave me that if X is a closed subset of Sn, X is a finite complex, then the sigma 1 minus n of Sn minus X is homotopic to the Spanier Whitehead dual. I'm writing Sn minus X, but what I really mean is some compact deformation retract of Sn minus X. That's what I really mean, but I'm writing Sn minus X nevertheless. And now I want some unpointed version. So I will take X, which is unpointed inside Sn, and uh, I will put a disjoint base point. So this will go inside Sn like this. This so X is going to miss some points in Sn. So this plus will go to this embedding will be such that the image that you take a disjoint point from the image of X and call it infinity. So this plus corresponds to infinity. But if I write it like this, Then you see, if I take d of x plus, this is equivalent to sigma 1 minus n of Sn minus x plus, but remember the disjoint point is the infinity point. So if I remove that by stereographic projections, I have Rn. So that is actually the same as sigma 1 minus n of Rn minus x. Okay, so that's same as sigma 1 minus n of Rn minus x. All right. Now I will do something uh, a clever trick. I will look at Rn minus x to Rn and look at Rn mod Rn minus x. Okay, so this is so this Rn minus x. The way I am thinking about it is I have taken some neighborhood of x and I'm looking at the complement of that neighborhood. Okay, and so when you look at it inside Sn, that actually becomes compact. So uh, so I'm doing it like that. So that's the way I'm thinking about it. But Rn is contractible. So so as a stable homotopy type, I see that Rn mod Rn minus x is actually equivalent to the suspension of Rn minus x. So another way of saying this implies that the Spanier Whitehead dual of x plus is equivalent to now one suspension goes away because I will replace the Rn minus x with Rn mod Rn minus x. So one suspension will go away and I will get sigma minus n of Rn mod Rn minus x. All right. Now suppose x is a closed manifold. Suppose x is a closed manifold. So suppose x is a closed manifold. So then I can take a tubular neighborhood. So then you can take a tubular neighborhood. Then you can take a tubular neighborhood U, and then you see that Rn mod Rn minus x, this actually is homotopy equivalent to U mod boundary of U. Okay, that is just you you radially deformation retract outside X. Now this U is the disk bundle of the normal bundle of the embedding. So the normal bundle N is the normal bundle, and U is the disk bundle of normal bundle. And so this is U mod boundary U is the disk bundle of the normal bundle mod the sphere bundle of the normal bundle, E of n mod S of n, or this is the Tom space of n. Okay, so let's go to the next page. So I have this again d of x plus n mod Rn minus x, which is again equivalent to sigma minus n of the Tom space of the normal bundle. Now the vector bundle, so the normal bundle, I can write this as n minus tangent bundle, right? n minus tx. I can write it as n minus tx. So if I write it like this, then what is the Tom space of n minus tx? Tom spectrum of n minus tx. This, remember, you can always take some, as we have commented before, whenever you have a trivial summand, you can just take it out as a suspension. So you can write it this as sigma n of the Tom spectrum of minus dx. That tells you that d of x plus is equivalent to, so now these two n's cancel, the Tom spectrum of minus dx. This is the theorem. This is the statement of Atiyah duality. This is the theorem in Atiyah duality. Finally, uh, what I can say is that um, if uh, if X is orientable, the manifold, then uh, then I can write this 8z smash Tom's this Tom space Tom spectrum of minus dx is orientable and dimension, you mention, let's say dimension a or dimension m. This is going to be equivalent to, and this is negative, so that to be sigma minus m of z mesh x plus. So I get that smash x plus isomorphic to sigma minus m of 8z smash x plus. Okay, now you take pi k, you take pi k, then I get on the left, I get you take pi minus k, and I will get h upper k. You see, homology of the Spanier Whitehead dual is just negative of the homology, so I will get h upper k of x on the left is isomorphic to. So what would I get here? H m minus k of x, which is Poincaré duality. So this is Poincaré duality. Stop. I said something, but if anyone asks, I can talk about it during the interaction session. So I'll stop there. And sorry for going over time.